So modelling with differential equations, as the name suggests, means we have some sort of differential equation which we use to model a real life situation, and maybe we need to solve it and work some values out. So the first thing to remember is that from the differentiation chapter, you use the chain rule to create your own differential equation. So that was in the differentiation chapter, I think the last section. So I don't know if you needed dx dy. It may be that you worked out something like dA dy and you'd multiply that by dx dA, for example. Yeah, so that's the differentiation. So you may be asked to create your own differential equation or show that the differential equation given is true. So let's say then that we have our differential equation, which is dx dy is some sort of function of y, so dx dy equals something like that, for example. Then you would use integration to solve it, and then what you would have is your function like that plus c, and when you've got plus c, you've got your general solution once you've worked out the once you've integrated it. And if we work out c, so if we are given values, so sometimes they may be what we call the initial conditions. If we are given values, initial conditions, to work out c, then we have what we call our particular solution. So this sort of brings together all the stuff that we've done in the integration chapter, and actually some of the stuff on differentiation, creating differential equations from the differentiation chapter. So it brings all those things together. So let's have a look at some examples. So here we have a differential equation which we need to solve, and the question says that we actually need to write p equals, and it tells us what form we need to get it in. It says initially the population was the size of 8, so that means that when t is 0, that p was 8. So that's probably going to be useful in some part of the questions. I'm just going to write those down. Part A, find a model for p in the form p equals a e to the power 3t, stating the value of a. Okay, so dp dt equals 3p. So separation of variables, so multiply both sides by dt and then divide both sides by 3p. I will get 1 over 3p dp equals dt, so this is like 1 dt. Integration symbol in front of both sides so we can integrate. On the left hand side I will try log of the bottom, so log of 3p, and that will give me 3 over 3p if I differentiate it, so I need a third here, equals, and then if I differentiate the other side, that will just become t plus c. Okay, so now what I need to do is to find c, because what I've got written here is the general solution. I want the particular solution, because you see there is no sort of c here. Well, there is a c, it's like the letter a, and we need to state the value of it, so we can't leave our answer with just the letter there. We need to work out its value, so that's what we're doing now. So we're told that initially the population is 8, so let's put those in. So 1/3 log, initially the population was 8, and that's going to equal initially 0 plus c. Okay, so that's nice and easy. C equals 1/3 log 24. I don't really need the modulus, it's positive. So now we can write our particular solution is going to be 1/3 log 3p equals t plus c, and c is 1/3 log 24. Now I'm going to times both sides by 3 to get rid of these thirds because I want to make p the subject, so I end up with log 3p. I'm going to dispense with the modulus, I don't need them anymore. This whole population is always going to be positive, equals 3t plus log 24. If I now raise both sides to the power e, so an e there and an e there, then I will have 3p equals e to the 3t plus log 24. Now if you've got sort of e to the power something plus something, that's the same as e to that times by e to that, so that will give us 3p equals e to the 3t times by e to the log 24. So the e and the log here will cancel out, just leaving you with 24. So my final answer, once I've divided by 3, because I've got 3p equals that, so now let's write p equals, it's going to be 1/3. Well, actually, let me write the whole thing out rather than do too many steps at once. So e to the 3t times by 24. Okay, now divide both sides by 3. So p equals 8 e to the 3t. So here's my solution to that equation, and it will be nice just to show the examiner stating the value of a equals 8. So we'll write that down as well, just to make the examiner's life a little bit easier. Right, I think the next bits of the questions are probably the easier parts now. Because of space, I'm going to do B, part B here. Find to the nearest 100 the size of the population when t equals 2. So this is easy. We just substitute 2 into our equation. So population equals 8e to the power 3 times 2, or to the power 6. So that will give us, we'll write down the full thing, then round it to nearest 100. So 8e to the power 6. That gives me 3227.4303. They want it to nearest 100, so we'll write p is 3200. So I'll just highlight that before we move on to part C. Now part C is asking, find the time at which the population will be 1,000 times its starting value. Now the starting value was 8, wasn't it? That's in the question. So starting value equals 8. So we basically want to find the time when the population is 8,000. So in our equation, we were put population equals 8,000. So 8e to the 3t. So this is just about working out what t is. So we'll divide both sides by 8. So I'll just swap it around. So we've got e to the 3t equals 1,000. Then from there we'll raise both sides, or we'll do the log of both sides. Let's do that over here. So I'll have the log of 8. Well, actually, oh no, sorry, I'm looking at the wrong thing. E to the 3t equals log 1,000. So the e and the log will cancel out, just leaving 3t. So I'll just put that down. 3t equals log 1000. So that means that t equals 1/3 log 1000. And actually, even without your calculator, you could say, well, actually this is the same as t equals the natural log of 1000 to the power third. That's the cube root of 1000, which is 10. 10 times 10 times 10 is 1000. So you could say actually t is just log 10, but because of the form they want to answer, I don't want to leave the time as log 10. So let's work out what log 10 is, or natural log 10. That is 2.3025. So t is 2. Now what does it say? Find the time. Just find the time. It doesn't say it. So 30. That's 3 significant figures, and it's hours. So 2.30 hours. Now if we change that to hours and minutes, so that will be 2 hours. So if I take away 2, what's left, times it by 60. So that's 2 hours, 18.155 minutes. So let's just call it 2 hours, 18 minutes. I think that's accurate enough. I mean, I don't need to work out the number of seconds. If I did, it would be 2 hours, 18 minutes and 9.3 seconds. If I really wanted to sort of, you know, show off, but I think 2 hours, 18 minutes is fine. Part D, elimination. State one limitation of this model for large values of t. Now what the model suggests is that as t increases, the population increases, which is fine, but this says that the population is just going to keep increasing. So if I put a value of t of 1,000,000 seconds, it's going to come up with a crazy size for the population. Now we know populations do not increase and keep increasing. There comes a point where they can't increase anymore. Maybe there's no food left. Maybe, you know, there's just not enough space. Something happens. There's a pandemic or a disease that stops them from growing any further. So if we wrote something like, you know, populations, or I suppose the population rather, specific to this question, the population will not keep increasing forever. Yeah, now it's probably only going to be a 1-mark question, so writing something like that would give you the mark. If it was 2-mark, you might want to give an example, e.g. why wouldn't the population keep increasing forever? E.g. there may not be enough space. I'm just going to put food, enough space for the population to keep increasing. Yeah, so, you know, putting a sensible reason might help as well. Okay, very last example of the very last section in this integration chapter. So let's have a look at this. This is about a tank where water is coming out like this, so it's dripping out of the tank. There's information here about the radius of the tank and the height of the water in the tank, and differential equations that we need to solve, find general solutions, find values of constants, things like that. So let's work through this. Part A. Well, actually, let's write down, let's read through it. So the first sentence, yeah, cylinder, diameter 10, so diameter 20, radius is 10 meters, flows out a rate which is proportional to the cube root of the volume. So I'm going to use those. Now if you think back to the differentiation chapter, if you had something that was decreasing, you used a negative sign. If you're talking about something being proportional, you would use a letter to represent that, something like K. Now they've already used K, so I'm going to use a different letter. So let me use capital letter A for my constant, and here cube root of volume, so cube root of V. And let's work through this. So we want to find dH dt. Well, let's write down what the volume is of this tank, pi r squared h. So radius is 10, so it's 100 pi h. We can find dV dH, so the change in volume over the change in height, which is going to be 100 pi. Okay, that's going to be useful. Now I actually want to find, let's write it here, I want to find dH dt. So far I've found dV dH. The reciprocal of that is dH dV. So if I were to multiply that by dV dt, then the dV's will cancel out and it will give me, let's sort that h out, it will give me what I want. So I've got the reciprocal of half of what I need here, so I can make that dH dV. Can I find a change in volume over time? Yes, from this sentence, all this stuff where I wrote negative root cube root volume A. Right, so let's do that. The change in volume over time, well, the volume is decreasing at a rate which is proportional to the cube root of the volume. There we go. That's straight from chapter 9, I think it is, the differentiation. We know what the volume is, so dV dt, you could say is negative the constant times by the cube root of the volume, which we've just got up there, which is 100 pi h. So that means that dH dt is equal to dH dV, which is 1 over 100 pi, the reciprocal of dV dH, times by dV dt, which is negative a cube root 100 pi h, like that. We need to get it into the form negative k root cube root h. Now we can do that because this bit here, we can write that as cube root 100 pi times by cube root h. So putting that all together, we'll get something like dH dt equals negative a, and then we'll have, actually let's write the a at the top, we can put that all together. So we'll have negative a cube root 100 pi over 100 pi times by the cube root of h. So it's in the format that they want, and this bit here, that's k. So we'd write down something where their k equals my constant cube root 100 pi over 100 pi. So that would be our part A. Part B, and we'll do part B over here, show that the general solution, so general solution means that we're not working out what the constants are, to this differential equation. Now which one? The one that we've just done? No, this one. Yeah, so it's very important that you're not trying to do it with the one that you've worked out, but the one that's given this differential equation may be written in that form. So we need to start with a dh dt. So this is all about solving it using the separation of variables and then making h the subject. So if I put all the h's on one side and the t's on the other, so I'll have 1 over cube root h dt. Now I could take the constant over as well, because the constants can go on either side. I've decided to leave it where it is, not dt, dh. So I'm going to leave the constant there and then have dt like this. Now I want to integrate both sides, so an integration symbol here and here. Now I'd probably, well, I would write that as h to the power negative a third, so it's easy to integrate. So h to the power negative third integrated, so you add 1 to the power, so that's going to be h to the power 2/3, and you divide by that new power, so you got 3 over 2 equals negative k integrated with respect to t would be negative kt plus my constant of integration. So I'm going to call that b. I'm just going to go through the alphabet, capital letter B for my constant, and then from here all I need to do is to make h the subject. So step number 1, I'm going to divide both sides by 3 over 2, so I've got h to the power 2 over 3 equals negative 2/3 kt plus 2/3 b, and then to make h the subject from there, I raise both sides to the power 3 over 2. So and then I'm going to just swap these over so that it's the same way round as what they want in the question. So all of that is raised to the power 3 over 2. So that's a nice little trick, that if you've got a power and you want to basically cancel that power out, you raise it to the reciprocal power, yeah, which is what we've done. So that basically becomes power 1. So we've got what they want in the right format. So I'm just going to say now over here where, now what have they got? P, their P equals 2/3 B, and what they've got for Q I've written as negative 2/3 K. Yeah, so it's important that we do that so that, you know, they can match up what we've written, and it makes the job easier for the examiner as well. So let's just rule this off, because we're going to have lots more working, I think, in part C. So part C, it tells us that initially the height of the water is 27, and 10 minutes later, T is in minutes, not seconds or hours, the height is 8. Use these to find the values of P and Q. Right, so we're going to be substituting in, first of all, the 0 and 27 into this equation here. Yeah, right, so H is 27 and T is 0, so you'll basically get Q times 0 to 3 over 2. Right, so that will give us, well, P to the power 3 over 2 equals 27. So reciprocal power, P equals 27 to the power 2 over 3. So it's the cube root of 27, which is 3, and that is squared. So P is 9. Let's just put that there. And then we're going to substitute in the other two values, so the 10 and the 8. And we can put P in as well now, and then use that to find Q. So when the height is 8, we will have P, which is 9, minus Q times T, so that's 10Q, thank you, to the power of 3 over 2. Okay, so we're now going to raise both sides to the power 2 over 3. So 9 minus, thank you. Just tidy out that 9. Right, now the cube root of 8 is 2, 2 cubed is 4, so we end up with 4 equals 9 minus 10Q. That should be easy enough. So we will take away 9 from both sides, so we end up with negative 5 equals negative 10Q. So Q is not 2, it's a half. So Q is a half, and we'll just highlight that there. And finally, part D. What's part D asking for? Find the time in minutes when the water is at a depth of 1. Right, so we can write our full equation. H equals, now P was 9, 9 minus a half T, because Q was a half, to the power of 3 over 2. We're finally there. Find the time in minutes when the water is at a depth of 1. So H is 1. 9 minus half T to the power of 3 over 2. We raise both sides to the power 2 over 3, so that remains as 1. So we'll have 1 equals 9 minus a half T. Let's go down here, we've got a bit more space. So we take away 9 from both sides. Negative 8 equals negative half T. We're almost there. So negative a half times what will give you 8. I think that's, or negative 8, I think that's going to be 16. So it will take 16 minutes. Find the time in minutes. So 16 will do. We'll put 16 minutes. We have now completed what I would say is probably the hardest chapter in the book. And the rest of chapters, I think, are a little bit more straightforward. You really want to be able to master this integration chapter. Right, so now the way to master the integration chapter is to do lots and lots of practice. And there's lots of practice questions in the book. There's lots of practice questions you can get online, even from different exam boards as well. Once you've mastered it, it does really boost your confidence. You really need to know what's going on in this integration chapter. So make sure you complete all the questions in that exercise, plus the mixed exercise as well. And it might even be worth going back to the differentiation chapter, and I'm not sure what section that is. Rates of change, that's it. Section 9.10, so I'll just write that down. It might be worth dipping into that. Rates of change, and that's you'll find that on my 9.10 video on differentiation. So it's worth dipping back in that to just help you out on doing this final section.